Okay, so this slide summarizes the equations that we've learned so far with regard to inductors. The first is the definition of self-inductance, L, and L is measured in henries. And the second describes the expected induced EMF for a given rate of change of current and knowing what the self-inductance is of the inductor. And the induced EMF will always oppose the change in current. So the top image on the right shows the current increasing, and the induced EMF is opposed to the change. And the second case shows that the current is decreasing in the circuit, and then the induced EMF is going to be in the same direction as the current to oppose the change. So when the current is increasing, induced EMF is opposed to the current. When the current is decreasing, the induced EMF is in the same direction as the current to keep it going. And in both cases, it's opposed to the change in the current. And the next thing we want to do is consider some circuits that have inductance present. And the first circuit that we look at is called an LR circuit or an RL circuit. And our process for analyzing this circuit is very similar to how we treated our C circuits back in an earlier chapter. And what's shown in the image is a circuit where the switch has not yet been thrown. And when we throw the switch to position A, the current is going to begin to flow in the circuit. So I'm going to throw the switch in an animation. And the switch goes to position A, and then the current begins to flow in the circuit. And so we've got a current which is increasing as we would expect once we connect the battery to the resistor. But since the current is increasing, there's going to be resistance in the inductor to that change in current, which will produce an induced EMF in opposition to that current flow. And we can use this picture of the circuit to analyze the time dependence of the current in the circuit. So the current isn't going to instantaneously go to its expected value of the EMF, the voltage over the resistance. Instead, it will take some time to reach the maximum current in the circuit. And to analyze this circuit, we can use Kirchhoff's loop rule, where we begin our analysis by choosing a point in the circuit. I'll choose the point which is at the lower left, and then we're going to step around the circuit in the clockwise direction, and this will follow the current around the circuit. So applying Kirchhoff's loop rule, we first encounter a potential gain of plus E, and then a potential loss across the resistor of IR. And then we encounter another potential loss across the inductor, which is the induced EMF. And the induced EMF is equal to L di dt, so we subtract a potential loss of L di dt as we step over the inductor. And then we're back to our starting point again. And so this is just an application of Kirchhoff's loop rule, but now we've introduced a new circuit element, which is that of the inductor. And this equation can be rearranged to write it as it is on the right. And then this is a first-order differential equation that can be solved using the method that we did for the RC circuit. And so to do this, we would separate variables and put every term involving I on the left-hand side of the equation, and then every term involving t, and there's only one, on the right-hand side of the equation. And once we separate variables, we can integrate the left and the right, and when we integrate the left-hand side, we're going to get a natural log function. And then when we plug in the limits and rearrange, the equation that results is the equation that's shown in the red box. So you might try that as an exercise. You don't have to, but if you like to do integrations, it's a good practice to be able to integrate the expression so that you can see that the result is the equation in the red box. And this equation describes the time dependence of the current in the LR circuit. And the equation you might recognize as looking quite similar to the equation that we saw for the RC circuit. And this equation you don't need to know how to derive. It'll be on the equation sheet for the exam, and you can just make use of it. So for an LR circuit, we find the time dependence of the current is described such that we expect the current to start at 0, and that's because using this equation at t equal to 0, I is equal to E over R, 1 minus E to the 0, and E to the 0 is just 1. And so when we first throw the switch, we see no current flowing in the circuit, and asymptotically, as t goes to infinity, then we can get a picture of where the current is headed. We'll have 1 minus e to the negative infinity, and that's 0. And so this will give us just e over r. And so our expectation is that after a certain amount of time, the current is going to reach its full current of the EMF over the resistance, which is what we would expect if there was no inductance in the circuit. So it's going to get to what we would observe if we just had a battery and a resistor, but it takes a little bit of time to rise up to that value. It doesn't happen instantaneously. And as a measure of how much time it takes to reach its maximum value, we can use a time constant as we did for an RC circuit. And this time our time constant is defined to be the inductance in the circuit divided by the resistance. And if we make the substitution of this time constant in our original equation, then we get the equation that's shown in the red box here. And so this is our go-to equation then for figuring out how the current varies in the circuit as a function of time. And the time constant acts as a figure of merit in the same way that it did for an RC circuit. We find that the current will have risen to 63% of its maximum value at one time constant. And that's shown in the picture. After a time of one time constant, we're at 63% of the expected maximum current. And so as a quick calculation, the time constant is an easy thing to calculate. We take the inductance in the circuit divided by the resistance, and then we'll have a feel for how quickly the current is going to rise. One thing to notice about the time constant is that it is proportional to the inductance. So if we have more inductance in the circuit, the time constant is going to rise, and it's going to take longer for the current to build up to its maximum. The other situation we encounter with an LR circuit is that if we have a current flowing in the circuit and we now switch the battery out of the circuit, then the current in the circuit is not going to immediately drop to 0 if there is inductance present. Rather, it's going to fall off gradually towards 0, and that's illustrated in the circuit diagram. If I throw the switch to position B, now the current in the circuit that was flowing begins to decrease, and due to that changing current, there's going to be an induced EMF in the inductor opposed to that change that is going to continue to force the flow of current for a while. And to analyze the time dependence of the current in this case, we would again apply Kirchhoff's loop rule to this new circuit, starting at the red dot and moving in the direction of the current flow, so moving clockwise around the loop. We first encounter the resistor as a potential drop of negative IR, and then we encounter another potential across the inductor, which is negative L di dt. And since di dt is less than 0, that's actually a potential gain across the inductor. And if we rearrange this expression, it gives us the equation on the right, and then we can apply separation of variables and integrate. And the result of this process is that the current is going to fall off exponentially as a function of time, and we see the time constant present, so we can simplify this expression. And again, the time constant represents a figure of merit. We find the current will fall off to 37% of its maximum. If I naught is where it started, then it's fallen to 37% of the maximum within one time constant. Okay, so I'm going to work an example. This is problem 35 from chapter 30, and this example shows a circuit that had a current flowing in it. It says at t equals 0 seconds, the current in the circuit is I naught. So at t equals 0 seconds, I is equal to I naught. But now the circuit has been closed and the current is going to begin to fall as a function of time. And the question is, at what time will the current be half of its initial value? And other givens in this problem are the two resistance values that I'll label R1 and R2, and then the inductance value. So R1 is 200 ohms. R2 is 100 ohms, and L is 75 millihenry. And with this information and knowing the behavior for the current falling in the circuit, which is that I is equal to I naught e to the negative t over tau sub L, we can solve for the question, which is to figure out at what time will the current have fallen to half of its initial value. And to simplify our circuit so that it looks more like just a single resistor with an inductor, we can combine the two resistors in series. And so we can redraw our circuit with a single resistor. And so that resistance R12 is equal to, because they're in series, R1 plus R2. And that would be 300 ohms. So we've got 200 plus 100 equals 300 ohms. And the time constant of this circuit, tau sub L, is equal to L over R12, the equivalent resistance. And that could be calculated, but I'll leave it symbolically here. And then the question is, we want to figure out how long it takes for the current to reach half of its initial value. So we would have I naught over 2 is equal to I naught, and then our goal is to solve for t the time that it takes for the current to go to that value. And the two I naughts are going to cancel from side to side. So this will give us 1/2 is equal to e to the negative t over tau sub L. And this will be log of 1/2 is equal to minus t over tau sub L, or t is equal to negative tau sub L log of 1/2. And the time constant equation is the L over R12. And so then we would just calculate this expression. And so I'll move to the next slide to do that. So we've got t is equal to negative L over R12 log of 1/2. And then plugging in the numbers, this is negative 75 millihenries over 300 ohms times the log of 1/2. And this will equal 1.7 times 10 to the negative 4 seconds. And so graphically, this is the current flowing in our circuit, and we've shut the circuit off, so it starts at its maximum value of I naught and is falling off exponentially towards 0. And after one time constant, we know the current will have fallen to 37% of its maximum. So to fall to half of its maximum, that time must occur sooner than one time constant. And that's the time that we solve for in this problem. So this is the t value that we just found to be 1.7 times 10 to the negative 4 seconds. So in this circuit, it's not taking very long at all for the current to go to 0. And that's an example of an LR circuit. Okay, so a figure of merit then again for LR circuits is this time constant. This is the inductive time constant, which is equal to L over R. And the important thing to think about when you're using this time constant is it measures the rate at which the current is either going to increase if the current is building in a circuit or decrease if the current is falling. And the greater the inductance, the greater the time constant. And then when we come back, we'll look at a different type of circuit, which is an LC circuit.